3, 2, 1.
Okay, so you sent in a whole bunch of stuff on gamma ray bursts.
GRBs.
Yeah.
GRBs.
The most luminous events in the universe.
And the question you're asking is basically, do these things?
These incredibly powerful events.
Yeah, do they actually bend space-time as they're traveling? They're putting out more energy than the sun will in its entire lifetime in just seconds.
Yeah, it's a mind-boggling amount of energy.
So you got to figure out if it's enough to make a measurable warp in space-time based on what you sent.
Right, and you've got some really interesting articles and research here.
Yeah, so let's dive into it.
All right, well, first we need to kind of clarify what we're talking about with GRBs.
Yeah, for sure.
So we see these boosts in two main varieties. You've got the short ones, which are likely from things like neutron stars merging.
Oh, wow.
Or black holes merging.
Okay.
And then you've got the longer ones,
right,
which are thought to come from really massive stars when they collapse at the end of their lives.
So way different origins. Yeah, and the energy output can vary wildly too. We're talking anywhere from 3 times 10 to the 46 erg.
10 to the 40s.
But to a mind-blowing 10 to the 55 erg, and the durations are all over the place too.
Okay, so some are quick bursts, some are longer.
Exactly, but even a kind of typical GRB.
If there even is such a thing.
Right, good point. But even a relatively average one is still spitting out something like 3 times 10 to the 44 joules.
That's just an insane number.
Oh yeah, and that's vastly more energy than you get from a supernova.
Wow, so these things are really packing a punch.
Absolutely, and some of them like GRB 2217009A.
That one was nuts.
Oh yeah, it was so bright it basically overwhelmed our detectors.
Crazy, and that energy isn't just going everywhere, right? It's focused.
Right, you've got these beams.
Like beams of energy.
Yeah, powerful jets.
And we can even estimate how wide those beams are, right?
Yeah, by looking at the afterglow of the GRB, you see these things called jet breaks.
The dip breaks.
And that gives us a clue about the 5 degrees. But it can range from 2 degrees up to 20 degrees.
So some are really focused and some are wider.
Exactly. And for the low luminosity ones, like the one you mentioned, 22109A,
right,
they can even be wider than that.
Okay, so that focusing all that energy into a beam, what does that mean for how much energy is packed into that space?
So that's where this concept of energy density comes in, and at a distance of about 1 parsec.
Okay.
Your sources here suggest that the energy density inside a typical GRB beam is something like 2.6 times 10 to the 15 joules per cubic meter.
Okay, now that's a big number.
Oh, it's huge.
But is it enough to do something to space-time?
Well, to answer that, we need to consider this thing called the Planck energy density.
Uh-huh.
This is where we think quantum gravity starts to really dominate.
Okay, so the realm of the super tiny.
Right, and that Planck energy density is a whopping 9 times 10 to the 116 joules per cubic meter.
So how does the GRB beam compare to that?
Even at its most intense, right near the source, the GRB beam is still over 100 orders of magnitude weaker than that Planck scale.
Whoa, so not even close.
So not even in the same ballpark.
So does that mean it's not doing anything to space-time?
Well, not so fast. Einstein's theory of general relativity tells us that gravity is essentially the curvature of space-time.
Okay.
And that curvature is caused by mass and energy. Anything with energy can warp space-time.
Even light.
Exactly. Even light bends because its energy is equivalent to mass.
Whoa, so that means the GRB beam, even though it's not at Planck scale energy,
right,
it still should be bending space-time at least a little bit.
In theory, yeah, but we got to consider how that beam is behaving as it travels. It's not staying all bunched up.
Right, it's spreading out.
Exactly. It's like stretching a piece of taffy. The further you stretch it, the thinner it gets.
Okay.
So the total energy of the beam stays the same, but the energy density decreases as it spreads out.
So that means the bending of space-time would be strongest near the source.
Right, where it's most concentrated, and as it travels, that effect gets weaker.
Okay, and the beam itself isn't just spreading out in all directions, right?
Right.
No, it's expanding in a cone shape, which means its volume is increasing.
Okay.
And that further reduces the energy density. So any bending would be mostly along the path of the beam.
And very subtle.
Very subtle, yeah. There's this really interesting idea that super intense light beams might actually have some self-gravitational effects.
Like they bend themselves.
Yeah, a kind of self-focusing. But even in GRBs, that would be incredibly weak and really hard to observe.
So what about quantum gravity and things like gravitational lensing? Does that play a role here?
Well, we already talked about how the energy density in the beam is way below the Planck scale.
Right.
So those direct quantum gravity effects during the beam's travel are probably not happening.
Okay.
Now, GRBs themselves can be lensed.
What do you mean?
So if there's a massive galaxy or a black hole between us and the GRB, that object's gravity can actually bend the GRB's light.
Oh, like a magnifying glass.
Yeah, sort of. It acts like a lens and distorts the GRB's image.
That's so cool.
It is, but the GRB beam itself acting as a lens, that's not something we've seen or really expect.
Okay.
It's just too fleeting, and the beam is too spread out at those distances to have a noticeable lensing effect.
So it seems like the really dramatic space-time warping is happening right at the source of the GRB?
Exactly. That's where you have this insane concentration of mass and energy, which can lead to black hole formation and the launch of these jets.
Right.
And compared to that, the beam's effect on space-time as it travels is tiny.
Okay, so it's like the source is the main event, and the beam is kind of a sideshow.
Yeah, that's a good way to put it. And our understanding of all this comes from general relativity, which is a classical theory.
Classical.
Yeah, meaning it might not be the whole picture, especially at those extreme energy densities you find at the GRB source.
So there might be more to this story.
Definitely. And there are these things called energy conditions in general relativity.
Energy conditions.
Yeah, they basically help us define what kinds of energy and momentum distributions are physically reasonable. So it gets pretty complex, but it's all about making sure our models of these extreme events make sense.
Okay, so let's sum this up for everyone out there.
All right.
So GRBs, these incredibly powerful bursts of energy, they should be bending space-time as they travel.
Yeah, based on what we know about energy and gravity, that makes sense.
But that bending is probably super tiny, and we haven't actually observed it yet.
Right. The real space-time warping action is happening back at the source where the GRB is born.
Right, where things are super dense and intense.
Exactly. And even though the beam carries a ton of energy, its density as it travels is way lower than what you'd need to see significant quantum gravity effects.
Okay, so that kind of answers the question, but it also opens up a whole new set of questions, right?
Absolutely. I mean, we're talking about the most powerful events in the universe.
Yeah.
And we're still just scratching the surface of understanding them.
So considering how extreme these things are and how much we still don't know what other weird and unexpected ways might these GRBs be messing with the universe.
Yeah, I mean, think about it. These things are out there warping space-time, maybe in ways we haven't even thought of yet.
That's a pretty mind-blowing thought.
It is, and it just goes to show that the universe is full of surprises.
Definitely. Thanks for diving into this with me.
Anytime, it's been a fascinating discussion.
And to everyone listening, keep those questions coming, because who knows what other mysteries we'll uncover together.
Absolutely, the universe is waiting.